Okay, welcome to Let's Get to the Marks. This is part three of my walkthrough for aromatics in A-level chemistry for the physics and maths tutor pack. So check that out. Brilliant website, physics and maths tutor. Let's get into the last couple of questions in this pack on aromatics in A-level chemistry. This question is about nitrobenzene. Nitrobenzene reacts when heated with a mixture of concentrated nitric acid and concentrated sulfuric acid to form a mixture of three isomeric dinitrobenzenes. Write an equation for the reaction of concentrated nitric acid with concentrated sulfuric acid to form the species that reacts with nitrobenzene. So how does the sulfuric acid and the nitric acid come together to make the reactive species that nitrates benzene? So we want to write the formula for nitric acid, HNO3, the formula for sulfuric acid, H2SO4. They're the reactants. Now we want to create this species, which is our important species, the cation, the nitronium ion that is going to nitrate benzene. You can put the plus anywhere above there on the oxygen, the nitrogen, doesn't really matter. And that's NO2 plus. We're going to remove one of the hydrogens from the nitric acid, stick it on a water molecule to make H3O plus, and then we've got a hydrogen sulfide ion, SO4 minus. Super duper duper duper. There we go. We just need to balance it up. So I've got three hydrogens on the left. I've got four on the right. So I'm going to need to make five over here like that. And then I can put a two there and that's going to make five in total on the right. So we're now balanced for hydrogens and we can get on with the next part of the question. Okay, part B, name and outline a mechanism for the reaction of this species with nitrobenzene to form 1,3-dinitrobenzene. So what they're saying is you've got the NO2 plus, the nitronium ion that they talked about in the first part of the question. They're saying name the mechanism and outline how what I've circled there, the NO2 plus, attacks normal nitrobenzene or 1-nitrobenzene to form 1,3-dinitrobenzene. So let's write out the mechanism for that. Once again, pause the video, have a go yourself on some scrap paper, and then unpause and watch the walkthrough. Okay, so here we go. We've got a nitronium ion here, the NO2 plus. Now that's positive. We've got that electron-rich dense area, which is the delocalized ring on the nitrobenzene. That's going to donate a pair of electrons and join it to the nitrogen atom on the nitronium ion. Now, what we need to show here is a broken ring. Nothing dodgy about that. We just need to show a horseshoe with a positive symbol in the middle, and that is our broken ring. So first I'm going to add in our nitro on carbon 1. So we're looking to attack carbon 3, just working out with these horseshoes. One thing, it's a bit hard on the computer, but you've got to be careful that you don't make the horseshoe too big. You must make sure that the ends of the horseshoe do not cross the 2 points around the bond or around the carbon you're adding to. So anyway, there's my horseshoe broken. You're going to get a mark for that. You're also going to get a mark for showing that at the same time the hydrogen atom is joined with the new nitronium ion onto the same carbon. That hydrogen atom is then going to restabilize the ring by donating a pair of electrons to fix the ring, and we show that from a curly arrow. Make sure your arrow has a little curl in it. And now the ring is completely reformed. You don't get any marks for this normally in a mechanism. This is showing the final product. You won't get marks for that, but that's your 1,3-dinitrobenzene. Of course, that hydrogen ion that's been released is going to later on join with the hydrogen sulfide from up above in the first reaction and reform, which proves that sulfuric acid is a catalyst in that first reaction. Awesome. So your marks here were for the curly arrow from the ring to the nitronium ion, and then the arrow returning to refix the broken ring with a positive symbol, and that would get you all those marks. This is electrophilic substitution because a hydrogen atom is being substituted for NO2. All right, let's move on to the next question. The dinitrobenzenes shown were investigated by thin layer chromatography known as TLC. We've got 1,2-dinitrobenzene and 1,4-dinitrobenzene shown here in a diagram. In an experiment carried out in a fume cupboard, a concentrated solution of pure 1,4-dinitrobenzene, that's the one on the right, was spotted on a TLC plate, coated with a solid that contains polar bonds. Hexane is used as the solvent, and it's been put in a beaker with a lid. The lid stops evaporation of organic solvents like hexane that have low boiling points. The start line has been drawn, and the final solvent front are shown in the chromatogram in this diagram below. So we've got our start line and we've got our solvent front. Use the chromatogram in the diagram above to deduce the RF value of 1,4-dinitrobenzene in this experiment. So that little circle, okay, is how far the 1,4-dinitrobenzene moved up the TLC plate. You can see how far it's moved up the start line. Bearing in mind that the RF value is the distance the spot has traveled, so how far that spot has traveled compared to the whole distance of the solvent front, we can see that that spot has gone over halfway, right? So if you do distance the spot's traveled divide by the solvent front, you're going to get like 0.6, 0.7. It looks like it's gone over halfway. Okay, if it only went halfway, you get 0.5, less than halfway, you get 0.4, 0.3, etc. So you can see the distance it's traveled is over half. So straight away, when you look at this multiple choice, it's not going to be A or B because they're saying it's traveled less than halfway, and C is about halfway. It's gone more than halfway, so the answer has to be D. We don't even have to get our ruler out and carry out the calculation. Okay, super duper duper. Let's zing to the next question, peeps. Right. State in general terms what determines the distance traveled by a spot in the TLC. So, what factors determine how far a spot travels? Remember, there was a hexane solvent. Well, it's going to be how well our substance or our spot dissolves in the solvent. Now, another way of saying that is how what's its relative affinity for the mobile phase or the solvent compared to its retention in the solid phase. So what happens when substances move? They spend some time in the mobile phase, which is the solvent, and some time they spend retained on the solid, which is the stationary phase. So it's the relative affinity of each chemical to the solvent or the mobile phase, okay, compared to its retention on the stationary phase. Will tell you how far it moves. So if you have greater affinity for the mobile phase, you're going to move further up the paper, or the TLC plate in this case. To obtain the chromatogram, the TLC plate was held at the edges, placed in the solvent beaker in a fume cupboard. The lid was then replaced. Give something else they need to do. Just make sure when you put the plate in that the solvent is below the start line. If the solvent is above the start line, then the spot's going to dissolve into the solvent and they won't get carried up the plate. So we need to make sure the solvent is always below the start line. Otherwise the spot will run, and what that means is it will just dissolve into the solvent and it won't move up the plate, and we won't basically be able to calculate the RF value, etc. Okay, let's zing now to part F. So a second TLC, thin layer chromatography experiment, was carried out using 1,2-dinitrobenzene and 1,4-dinitrobenzene. So they used both spots and ran them together. An identical plate was used in the exact same conditions with the same solvent. Remember, that solvent was hexane from the first experiment. In this experiment, the RF value of 1,4-dinitrobenzene was found to be greater. That means that 1,4-dinitrobenzene moved further than 1,2-dinitrobenzene. Deduce the relative polarities of 1,2 and 1,4 and explain why 1,4-dinitrobenzene has a greater RF value. Well, let's think about the solvent here. The solvent is hexane. What do you know about hexane? What's its molecular formula? Well, you should know hexane has the molecular formula C6 times by 2, add 2 as it's an alkane, so we've got H14. And you should know the carbon-hydrogen bond is a non-polar bond. There's not a big difference in electronegativity, so this is a non-polar solvent. So the thing that moves further is more of a non-polar molecule. Non-polar substances dissolve really well in non-polar things. Polar substances dissolve well in polar solvents. So the fact that 1,4-dinitrobenzene moved further up the plate, had the greater RF value, means it's less polar, it's non-polar. 1,2-dinitrobenzene, dinitrophenol must be more polar because it's moved further up the plate. So the solvent, why am I putting DMP? It's dinitrobenzene. It's not dinitrophenol. Don't ask me why I put DMP. That's just dumb. Okay, so explanation here. The solvent's non-polar. As 1,2 dinitrobenzene had a lower RF value, it traveled a shorter distance, so showing it had less affinity for the solvent. That means that it doesn't like non-polar things. It prefers polar things, which means that 1,2 DMB is more polar, okay, than 1,4. 1,4 preferred the non-polar solvent, hence why it moved further, had a greater RF value because it had greater affinity for the non-polar solvent than 1,2 did. And that means that 1,4 is more non-polar in its characteristics. Super. Beautiful, beautiful, beautiful. Okay, so that's going to get you both your marks. Let's move on to the next question. And by the way, I shouldn't have put DNP there. That stands for phenol. It should have been DNB, but never mind. A third TLC experiment was carried out using 1,2-dinitrobenzene. An identical plate to that in part C was used under the same conditions, but the solvent used contained a mixture of hexane and ethyl ethanoate. So we now got our non-polar solvent, C6H14, just made of carbon and hydrogen, similar electronegativities, so no polar bonds involved in that molecule. But they've also this time mixed ethyl ethanoate, which is an ester, okay, made from ethanol and ethanoic acid, bonded together in a condensation reaction. And what we know with this molecule is you get the ester link, which has a CO and the carbonyl bond as well, the COO bond. And of course, there's a big difference in the electronegativity of oxygen and carbon. So we're going to have a delta positive carbon and some delta negative oxygens there. I've circled it in green. So this is going to be a polar molecule. So now our overall solvent is got some non-polar characteristics and polar characteristics. The student stated that the RF value of 1,2-dinitrobenzene in this third experiment would be greater. Are they correct? Justify it. Well, of course they're correct. We proved before the 1,2-dinitrobenzene prefers polar. So as this is a more polar solvent, the 1,2-dinitrobenzene is going to have a greater affinity for the polar solvent because it's now got ethyl ethanoate in it, and therefore it's going to move further in the mobile phase. It's going to move further up the TLC plate, so have a greater RF value. And there we go. That's another 2 marks, and that's the end of the question. Don't forget to like, share, subscribe. We're going to move on to the last couple of questions of this pack. It really helps if you hit the like and you leave any comments down below. Once again, I've written DNP here, which is wrong. It should be DNB, but you shouldn't be writing that anyway. I'm just abbreviating it for speed. You should be writing the full name out when you're talking about it, unless they allow you to use an abbreviation. Okay, let's move. Okay, question 6. Use your understanding of the bonding in benzene to identify the compound that has the most exothermic enthalpy of hydration. All you got to do here is check the distance between the double bonds. B, C, and D only have one single bond between the double bonds. So which one of these is going to be more stable? Well, B, C, and D are more stable because there's some overlap between those double bonds. They're close together, they overlap, and this increases delocalization. With A, there's a greater distance between the double bonds. There's 2 single bonds on each side in between the double bonds. So we have less overlap between the orbitals in the double bond, less delocalization, meaning it's not quite as stable a configuration as BCD, which means when you hydrogenate it and add hydrogen and turn it into cyclohexane, it actually does A will release more energy because it's less stable. So it's going from a less stable place to a more stable place. Whereas with B, C, and D, they have a smaller or lower exothermic enthalpy of hydrogenation because they are starting off from a more stable position as they have more delocalization, more overlap between their double bonds. Right, let's look at question 7. 1,4-diaminobenzene is an important intermediate in the production of polymers such as Kevlar and polyurethanes used in making foam seating. A possible synthesis for 1,4-diaminobenzene from phenylamine is shown in the following figure. So we've got phenylamine, and then in step 1, you can see we've had a molecule added to it. In step 2, we've had a nitro group at the bottom. And then in step 3, we have gone back to an amine and a nitro group. And then in step 4, we've turned that bottom nitro group into another amine. A suitable reagent for step 1 is CH3COCl, that is ethanoyl chloride. Name and draw a mechanism for the reaction in step 1. And there we go. Let's get into it. So for the mechanism in step 1, what's interesting here is this isn't the Friedel-Crafts where we're going to add that carbonyl group directly to the outside of the ring. So it's not Friedel-Crafts, which is where you get the carbonyl group use a halogen carrier to make it extra positive, so it's a real strong electrophile and it attacks the delocalized ring and temporarily breaks it. No, 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 no. This is added on to where the NH2 is, and it's substituted for one of the hydrogens on the NH2. This means it's actually a reaction of the side chain, and here you need your knowledge of amines reactions rather than your knowledge of directly of aromatic reactions. So with aromatic mechanisms, you've also got to know your other organic groups mechanisms, because they can be side chains coming off of the benzene ring, and it could be them that's getting attacked. See, I've circled here, it's the amine that's being attacked, not the delocalized ring. So what's going on here, we're going to draw our benzene out and we're going to put our amine with its little lone pair there. Okay, what's the lone pair going to be attracted to? Remember, positive can't move, only pairs of electrons can move. We've kind of got a delta positive carbon here on the ethanoyl chloride, so we're going to have our lone pair of electrons moving to form a bond here. So now what we need to do is we need to redraw the intermediate. Now what's going to happen after? Well, also that double bond is going to need to break. Why? Because carbon's in group 4, it can't have 5 bonds, and if it maintained the double bond to the oxygen and the new bond to the nitrogen, it would have 5 bonds. That's impossible. So it has to sacrifice a bond. So it temporarily breaks that oxygen bond on the carbonyl group. We know that's going to reform. You've got to know how to draw it in its new form. So we've got this new bond to the carbon, and then we've got that single bond to the O where it was a double bond, and we show the lone pair. I need to put a negative symbol there as well. We've got the methyl group coming off from the chlorine atom. So now we've only got 4 bonds around the carbon. That sounds great, but we've got this unstable oxygen, which is a lone pair and a negative charge. So what it does is it donates the lone pair back to the single bond to reform the carbonyl bond. So it's going to reform the COO, and the chlorine is going to break off. Now we look at our nitrogen, which is a nitronium or whatever cation. It's got a positive charge on it. Look, it's got 4 bonds. Nitrogen likes to have 3. You need to bear that in mind. So one of these bonds has got to go, and one of the hydrogens, any of these 2 hydrogens, is going to snap and donate its pair of electrons to that positive charge on the nitrogen atom, and that's going to stabilize everything there and mean it only has 3 bonds around it. So this is where the rest of the marks are, and you need all of these different bits, curly arrows and lone pairs to get the marks here. You do not need to, as normal with mechanisms, draw the final product unless explicitly or specifically stated in the question. You don't, but I always like to show you the final product. So here we go. And of course, what do you think the side group's going to be? We're going to have a hydrogen ion coming off, and you're going to have a chloride ion coming off, aren't you? So there we go. Wunderbar. Right, moving on, moving on, moving on, moving on. Part B, the product of step 1 was purified by recrystallization as follows. The crude product was dissolved in the minimum quantity of hot water. They put that in dark black. That means it's really important and part of the answer to the question. The flask was left to cool to room temperature, again in bold or dark black. And then it says the crystals formed were filtered with a Buchner funnel, and a clean cork was used to compress the crystals in a funnel. So again, and a little cold water was poured. Those bits in the bold black are really important and are keys to answering this type of question. So it says, give a reason why the minimum quantity of hot water was used. So you can tell what these questions are all going to be about, the things in bold. So why do we use only a little bit of hot water? Well, it's to ensure that the water is fully saturated with crystals. So we want to ensure full saturation of the solution with crystals. If you use lots of water, it would dissolve all the crystals and it wouldn't be a saturated solution. Now, for the second part of the question, it says the flask was cooled to room temperature before the crystals were filtered off. Why did they cool the flask to room temperature before the crystals were filtered? Well, as we decrease the temperature of the solution, the solubility of the liquid decreases. So its ability to hold on to crystals decreases, and we'll get crystals crystallizing. So what we're doing here is we're lowering the temperature, and as the temperature is lowered and cooled, the solubility of the solvent, the liquid, decreases. Its ability to dissolve the crystals decreases as its temperature decreases. And that means we'll get crystallization, and we'll make sure we get the maximum yield possible. Cool. So for the last part of this question, it says this slide that we're on at the moment, it says the crystals were compressed into a funnel. Why did they squish them up? This is to force the air to pass through the crystals. It removes all the air gaps between the crystals, and therefore the air is forced to go through the crystals instead of through the gaps in between. Right. A little cold water was poured through the crystals. So, why did we pour some cold water on the crystals? Well, that is to dissolve soluble impurities. So, any impurities that are soluble, they'll be dissolved in that little cold water and can be removed. Okay, part C. The melting point of the sample in part B was found to be slightly lower than the data book value. So the melting point, we're not quite fully accurate on that, suggests the most likely impurity to have caused this low value and an improvement to the method so that a more accurate value for the melting point could be obtained or would be obtained. Well, it's likely when we added that cold water to remove the soluble impurities in that last step, that water, which has obviously a melting point of 0 degrees, which is going to be less than our other substances, that's likely to have lowered the overall melting point slightly. That little bit of water and the removal of that water will ensure a more accurate result closer to the data book value. And we can do that by air drying it or pressing it between some filter paper using our fingers. Okay, the figure here is repeated. We've got the same reaction mechanism we looked at before, the exact same reaction mechanism from the start of the question. In an experiment starting with 5.05 grams of phenylamine and 4.82 grams of purified product were obtained in step 1, calculate the percentage yield in this reaction. Give your answer to the appropriate number of significant figures. So we have to remember the equation for percentage yield. This is a 3-marker. So percentage yield is equal to the actual mass divided by the maximum theoretical mass that we can achieve. Okay, times it by 100 and you'll get it as a percentage. Now, they told us in the question that we actually achieved 4.82 grams of purified product were obtained or achieved in step 1. So we know the actual mass is 4.82. We need to find out the maximum mass of purified product we can get. So we're going to need to use mass over MR times moles. We started with 5.05 grams of phenylamine. So we can find the moles of phenylamine by doing 5.05 grams divided by the MR. Now, what's the MR of phenylamine? Well, it has the formula C6H5NH2. So add that all together and you'll get 93. So we want to do 5.05 divided by 93, and that's going to give us 0.0543 moles. And that's going to get you your first mark. Now, if we look at the reaction mechanism, you can see from that reaction mechanism above, it's a 1-to-1 reaction. So we get, for every mole of reactant, phenylamine, we get 1 mole of product. So we're going to get 0.0543 moles of the product created. Ta-da! Now all we need to do is turn that 0.0543 moles of product into grams of product. We've got moles of product, we need to times it into grams. Now, how do you do that? Go back to your triangle, and we're going to need to do the MR of the product times the moles of the product. Now, what was our product? Well, in step 1, it was going from phenylamine to C6H5NHCOCH3. And if you add all of that up, you get an MR of 133. So we want to do 133 times the moles of 0.0543, and that will give us a maximum mass that we should have got of this product of 7.33 grams. So we should have achieved 7.33 grams if we started with 5.05 of phenylamine. Instead, we got 4.82, so we do 4.82 actual mass over maximum mass, which was 7.33 times 100, and you get something like 65.76. And then you can round to the appropriate number of significant figures. A-level, we tend to go to 3 significant figures, so like 65.7 or 65.8, 65.80, whatever. We ignore the 0, but there we go. Right, that'll get you 3 marks. Let's move on. We're on E. A reagent for step 2 is a mixture of concentrated nitric and sulfuric acid, which react together to form a reactive intermediate. Write an equation for the reaction of this intermediate in step 2. Oh my days. They are asking us to rewrite the old nitric acid and sulfuric acid equation. Dead easy. That forms a reactive intermediate. Well, it's just sulfuric acid plus nitric acid makes the NO2 plus H3O plus. We did this earlier in this pack, plus HSO4 minus. Balance it up. 2 in front of the HSO4 minus, 2 in front of the sulfuric acid. Bob's your uncle, Fanny's your aunt. Boom, equation done. Now, where are we? Yeah, so we are looking here. Next part to the question, name a mechanism for the reaction in step 2. This is going to be electrophilic substitution. And that's because you're swapping a hydrogen atom for the NO2 around the outside of the benzene ring. Right, suggest the type of reaction occurring in step 3. So we now got a zing to step 3 and identify the reagents in step 4. Let's zing to step 3, zing in. We're going from there and we are getting rid of the, we're going from the NH2 to NHC, we're going from NHCO CH3 to NH2. So what you've got to look here is we're hydrolyzing this bond. We're breaking this bond by adding water. And what in fact you're going to get, we're going to add a hydrogen to make NH2, and the OH from the rest of the water molecule will be smashed onto the side to make ethanoic acid with the CO CH3. So you should be able to see that. If you add water to here, you add a bit of H2O, one of the H's goes on to the NH2, which is attached to the benzene ring, and then the C carbonyl CH3 gains the OH from the water molecule and becomes ethanoic acid. Lovely jubbly. Let's go to the last part. And the last part of the question, and the last part of this pack, is identify the reagents used in step 4. So let's smash up to step 4 and look at what reagents. Well, step 4 is where we're turning the NO2 group, which you will see at the bottom here. We're turning that NO2 into NH2, into an amine group. And how do you do that? You do reduction. So we're going to reduce it and hydrogenate it. Now you could use hydrogen with a platinum, palladium or nickel catalyst, but in AQA they tend to like you to say hydrochloric acid with a tin catalyst, and that is used to reduce or you do hydrogenation. And there you go, that's the end of the pack, guys. So hit the like, share, subscribe. Let's get to the marks. I'll see you in the next video.
You're still here? It's over.